In this video, we'll be covering the review of the types of series that we know, as well as the tests or methods of evaluating whether a series is convergent or divergent. So, in the first setup, we're going to go ahead and talk about the types of series. The reason why we're going to talk about the types of series first is specifically because if you see this type of series, this is the series that you're going to go ahead and make the conclusion about and simply be done with the problem. So, the first thing you're going to look at is a potential of seeing a geometric series. Now remember, a geometric series is a series that looks of the form AR to the power of k. Now keep in mind that A doesn't have to be there, but it helps to have that A there. What's absolutely necessary is some number r to the value of k. Now we know that this particular series will converge when r is absolutely less than 1. All other cases, it will diverge. The geometric series will diverge if r is greater than 1 or less than a negative 1. Then, after we have the geometric series, we have a p-series. Now, the p-series I'm doing next specifically because it is mathematically similar to the way that we're going to look at this. The difference is that it's an algebraic function. So this one here is exponential in nature. It's r, some number to the power of a variable k. This one here actually has the variable in the base, and its exponent is a whole number. This is going to specifically converge when my p is greater than 1. So again, if my p-value happens to be negative, then it's going to diverge. If it happens to be equal to 1, it's going to diverge. But that's the convergency for a p-series. Our next statement is the harmonic series. Again, this is very specific. It's similar to that of the p-series. It's actually a specialty case of the p-series. And based on that definition, it also diverges, always. Lastly, we have the telescoping series, and the telescoping series is specifically a series that's going to alternate back and forth between two fractions, adding them up as we go. These series are generally convergent, and the reason why they are generally convergent is that you can utilize the limit of partial sums, evaluating the sum of all of the terms as they go, and you'll have a few terms in the beginning that are left over, and then all of the other terms will eventually tend towards 0. So again, this one's generally convergent. Now, out of these four types of series, harmonic is divergent. P-series can converge. The important ones to make note of is the geometric and the telescoping series. The reason why we want to make a note of those two is because those are actually the only two series that we can conclude what they actually converge to. So if I specifically ask you, or if somebody asks you to determine whether or not a series is convergent or divergent, and then follows up with, if the series is convergent, determine what it converges to. Well, if it is convergent, then and it's that type of question, then it has to be geometric or telescoping. Specifically because if it's not one of those two cases, we can't determine what it converges to without using the partial sums. So after we've talked about those four types of series, let's talk about the methods of evaluating the convergencies or divergencies of a series. So the first and most basic one, the one that we're going to avoid using almost at all costs, is the limit of partial sums, the limit of partial sums. And remember, the limit of partial sums is really just us taking the series, turning it into a sequence of s sub n, and then evaluating that limit. If that limit is equal to something, then we can actually conclude that yes, the series will converge, and yes, we can conclude what the series will converge to, because again, the sequence of terms is approaching a number such that that sequence is every new term in the series when adding up all the pieces. This is a very uncommon one. Again, I'm going to put a star next to it because it is a method that does tell us what it converges to, but that method is very, very uncommon in terms of it utilizing effectively. We really generally use this method to come up with new rules. So our new methods is the divergence test. The divergence test, recall, does not conclude convergence ever. So basically it says that if the limit as k goes to infinity of a sub k does not equal to 0, then the series a sub k diverges. And that's all it says. So if I can prove that the limit of the sequence doesn't equal to 0, it equals to 1, 5, 12, infinity, then I can prove then overall that the series will diverge. Your next test is the integral test. And again, the integral test specifically has it set up that we have to check first off three things: continuity, is it always positive, and number 3, is it monotone decreasing? And after we've checked those three pieces, then I can make the agreement of convergency with divergency of the series of, a sub k converges, implies directly that the integral of f of x converges. Okay, so keep in mind that these bounds are supposed to be the same, 1 to infinity, 1 to infinity. So if I can conclude that the integral is convergent, then I can make the conclusion that the series will also then be convergent. The next set of video notes that you're going to come across is a number of new tests that we're going to add to this list of methods. We may also add 1 or 2 new types of series to this list. So we're just trying to develop the methodology and the concepts of when we look at a series, can we determine whether or not that series is convergent or divergent? That's the entirety of this entire section of content. Can we determine if a series is convergent or if it is divergent? And again, the real big kicker is why. Which of these tests or which of these types of series are we using?